In this section, we'll discuss about cyclic structures of carbohydrates. We'd also define anomers and also blood group. Now, larger aldoses like glucose, fructose exist in aqueous solution as a six-membered ring or a five-membered ring. Six-membered ring is called pyranose and five-membered ring is called furanose. But in comparison with pyran is a six-membered ring with oxygen like this. Similarly, whenever glucose makes a ring structure, there is an oxygen in part of that ring, a six-membered ring. Fructose, on the other hand, usually makes five-membered ring, which is called furanose. Furan is like this. Again, it's a five-membered ring with oxygen as one of the members in the ring. So basically, when you make a solution of glucose in water, you get six-membered ring structure or pyranose ring. On the other hand, fructose or fruit sugar, when you make a solution in water, it gives a five-membered ring. In Haworth projection, the ring is considered to be flat, primarily a simplified version of ring structure. But we all know that six-membered ring is not really a flat hexagonal ring structure. It has, because those angles are 109.5. So it's actually chair-shaped structure is the most stable one. Now, what is anomer? Let me show you here with the formation of an anomer from non-cyclic Fischer projection. So this is what you're looking at is Fischer projection of glucose. Now, what happens is the oxygen of this chiral center, this oxygen with pairs of electron, it has pair of electron, it gets bonded to the carbon. That's the aldehyde group, and it makes a ring structure like this. And at the same time, this is since a six-membered ring, and it's called D-glucopyranose. Pyranose is the six-membered ring structure. This is also called hemiacetal because hemiacetal has one ether linkage and one alcohol linkage. If you focus on this bond, my blue arrow, this oxygen, when it is bonded to the carbon 1, then it's the ether linkage because there's a carbon in here, COC, that makes the ether linkage, and you have OH group, that's alcohol group, attached to carbon. So whenever you have an ether linkage and alcohol linkage to the same carbon, it's called hemiacetal. Now there could be two forms of it. This is called alpha anomer, where OH in carbon 1 is directed to the right. If OH group is directed to the left, it's called beta anomer. Now specific rotation of these two different isomers are quite different. For alpha, the rotation is plus 112 degree. And for beta, it's plus 18.7. So it's significantly different. Now, just to remind you what this specific rotation is, you know that these are all optically active. That means it rotates plane of polarized light. So in both cases, you see that, and in case of D-glucopyranose, that rotation happens to a much larger magnitude than with beta D-glucopyranose. Now, in solution, both forms exist. So there is an interconversion takes place from one to the other. And so overall rotation is observed to be plus 52.6. That means you get certain percent of alpha D glucopyranose and certain percent of beta D glucopyranose. That gives a number in between 112 and 18.7. Now, this is called mutarotation when interconversion happens from alpha to beta or beta to alpha, and finally it gives an equilibrium mixture. Now, some of the reactions are also we're going to discuss here. First, we talked about hemiacetal formation, which happens whenever it closes a ring structure from Fisher projection of non-ring structure. So here, this oxygen gets bonded to this carbon and this OH is formed. In this case, this OH is to the left because this is my right side, this is my left side. So even though actual ring structure is shown in chair conformation, but OH is on the left, and that's why it's beta. And I should also mention this to you. This is hemiacetal because you have ether linkage as well as alcohol linkage attached to that carbon 1. This is carbon 1. Let me highlight that carbon 1. Here I'm going to discuss problem number 20, page 487. The question is, D-glucose yields an optically active alderic acid on treatment with nitric acid, but D-allose yields an optically inactive alderic acid. Explain. So alderic acid is really having, it has two COOH group, both CHO on the top as well as CH2OH group on the bottom, both get oxidized by nitric acid to COOH. So the question is, why in case of glucose there is you'd expect optically active isomer. On the other hand, for D-allose, it would be optically inactive alderic acid. So let me first draw D-glucose. Now, in case you are not quite sure how to write down this structure or forgot about it, let me remind you with this. All altruist gladly, that's for glucose. We don't need mannose, so we got glucose and allose in this 3 name. Now you remember that CHO on the top, CH2OH on the bottom, and then each chirality center would have OH to the right or to the left. Now let's go about that, starting with chirality center number 1. Now here it would be right, left, right, and then left, right, like that. We don't care for the other ones because question is asking for allose and glucose. So the first one is allose and the third one is glucose on this line. Okay, now next chirality center would have 2 right, 2 left. Next chirality center would have 4 right and 4 left. So I don't worry about that. And next one would be for D, so all right. Okay, this is the last chirality center with D structure, so it would be all project would be arranged to the right. OH groups would be to the right. Now let me write down now D-allose to begin with. Allose is the first one. CHO on the top. CH2OH on the bottom. Now let's highlight these things. And you can see all the OHs are towards right. So OH 1, 2, 3, 4. So all these OHs are directed to the right when you hold CHO on the top and CH2OH on the bottom. Now you're treating it with nitric acid. So when I'm treating with nitric acid, the CHO becomes COOH, becomes alderic acid because they're telling you that. And then CH2OH also becomes COOH. And you have 1, 2, 3, and 4. So that's what we got, alderic acid from allose. So this one is allose. Allose. And this is alderic acid of allose. Now look at here, I can draw a plane of symmetry. Let's use a different ink. That splits the molecule into 2 identical halves. And you remember that when you have a plane of symmetry, it's optically inactive. So this is optically inactive because there is a plane of symmetry in the alderic acid of allose. You remember optically inactive, that means it doesn't rotate plane of polarized light. Now let me draw now glucose. Now glucose is given by this. So I'm going to write down first glucose structure, CHO on the top, CHO on the top, and then CH2OH on the bottom. Now you can see first one is right, OH is on the right for first chirality center. Next one is left, and next two are on the right. So this is glucose. I have hardly any space left here. So this is glucose. Now when I'm treating this with nitric acid, this gives me alderic acid. That means I would have COOH on both ends. So this is, we have COOH. The other groups remain intact. Then the left, then right, and right. This is the alderic acid coming from glucose. Now the question is there any plane of symmetry? Answer is no. No matter how you think about a plane, it's not going to split the molecule into two halves, two identical halves. So that's why there is no plane of symmetry. So I can say that no plane of symmetry. So that's why it's optically active. So no plane of symmetry means it's optically active. Now acetal formation, remember we mentioned that as soon as there's a ring formation in water solution, there'd be hemiacetal form because you'd have, in this location you'd have OH. But you can make an acetal. Acetal has two ether linkage. So how do I do that? React hemiacetal with methyl alcohol in presence of HCl and an acid. Of course, HCl is an acid in water, so that gives you H3O+. So that gives you OCH3 in this particular case. So there's two ether groups. This is the one ether group. This is COC. This is carbon, oxygen, carbon. That's one ether group. The other group would be let me use a different pen. COC. So that's COC. Okay, so these are the two ether groups, and that makes it acetal. Acetals are usually more stable than hemiacetal. They're stable in water. Ring doesn't open up or rotate to become alpha, beta anomers. That doesn't happen. These are also called glycosides, having ether linkage, two ether linkages. Now, glycoside linkage, has there are a lot of glycoside linkages in medical compounds. For example, trisaccharide plus steroid, this to treat heart disease. You'd see glycosidic linkage. Now, reduction reaction with sodium borohydride. Remember, sodium borohydride is a weak reducing agent. It offers H-. So that's how this reaction happens. H- goes in here in the first step of reaction, and then it goes in here, the electron pair, and finally it gives you CH2OH on the top. And it's called glucitol, a sugar substitute. Naturally, you can also get these in berries. Now, we can also readily oxidize a carbohydrate because of CHO group. So CHO group gets oxidized quite easily. That's Tollens reagent. In presence of Tollens reagent, CHO becomes COOH. So if you have galactose, that would also be oxidized, and it would be called galactonic acid. Now here we're showing you disaccharides. Now how that happens. Disaccharide means there are two monosaccharides combined together. Monosaccharide means basic sugar units. Like in this particular case, we're showing you alpha D glucopyranose bonded with alpha D glucopyranose. There are two glucopyranose bonded together through 1,4 linkage. And that's how you get maltose. Maltose has 1,4 linkage. That's what you see here. First one is coming from the left hand side compound, and fourth, this OH is coming from the second compound of glucose. In this slide, you're looking at hydrolysis products of cellulose. That means you're breaking down in cellulose to find out what makes cellulose. It's made up of sugar units or glucose units, but the connection is through beta. So that the beta bonded is that beta anomer. So it's the 1,4 beta linkage gives cellulose. On the other hand, in case of starch, which is also polymer of glucose, that's alpha, 1,4 alpha linkage. Properties are remarkably different because our enzymes cannot break down this kind of bond that exists in cellulose. So that's why cellulose acts as a fiber. On the other hand, starch, our enzymes can break down starch into smaller sugar units. Sucrose is made up of glucose and fructose units. They are bonded in such a way easily oxidizable CHO group is no longer available, for which you cannot oxidize it by any oxidizing agent. In other words, oxidizing agent doesn't get reduced, and that's why we call it non-reducing sugar. Now let me show you their bonding by first drawing glucose, and I'll show you how we can quickly draw fructose once you know the structure of glucose. So glucose, we already know, all altruis gladly, just GL is glucose. So in that way, we find out orientation of OH group. So let's first write down CH double bond O, and then CH2OH at the bottom. So I'm writing down now the structure of D-glucose. You would have first chirality center OH on the right, next one OH on the left, third one OH on the right, fourth one OH on the right. So that gives you D-glucose. So this is what you're looking at is D-glucose. Now if I want to change it to D-fructose, only thing that you have to keep in mind is the top group becomes CH2OH. So let's write down that CH2OH. The bottom group is also becomes CH2OH. It's already CH2OH. And not only that, the first chirality center, instead of having OH, it would have C double bond O in fructose. So that's C double bond O. So let me highlight this. And then rest would be the same as glucose. So it'd be OH, then two OHs on the right, and that gives fructose. So that's D. Let me write down here D fructose. Now, in solution, glucose makes a 6-membered ring. So I'll show you again that bonding. This oxygen, this hydrogen goes away from that oxygen, and it makes a ring structure with that carbon. So this double bond gets broken down, and then you'd have OH. This hydrogen from here gets bonded here. So you get OH. This is alpha anomer because OH is group in newly created center, that's carbon 1, is directed to the right. That's why it's alpha. On the other hand, ring formation in case of fructose will give OH directed to the other side. especially in making bond with this. So I'm going to make this. So showing this orientation to the left. How do I know that? Because that's the kind of bonding present in sucrose. So the beta anomer coming from fructose and alpha anomer coming from glucose. So alpha beta combination would give you sucrose. So these two gets bonded, water gets out, and it's an acetal formation, not hemiacetal, so it cannot be oxidized easily. And that's what we're showing you here. This is second position of carbon in case of fructose that combines with first position. This is number first position of glucose. So that's why we say 1, 2 prime glycoside linkage. Now here is the polysaccharide. Cellulose is made up of beta glycoside link. Starch has alpha glycoside link, and glycogen has alpha glycoside link. Of course, the bondage is between one location of one carbon, OH at location 1 with OH at location 4. Now, again, we're showing you two components of starch here. Is made up of amylose, about 20%, and amylopectin, about 80%. But if you look at the structure, amylose is pretty much unbranched glucose units bonded back to back. Whereas in case of glycogen is highly branched. This is amylopectin. Amylopectin as well as now here you're looking at deoxyribose that is present in DNA molecule. Now deoxyribose means oxygen is missing. This is the sugar unit. Remember, Raxel, ribose, arabinose, xylose, lysose. So that sugar unit is present in DNA, and that sugar has missing oxygen. So in other words, there is no oxygen here, rather there is carbon here. So that's why it's called deoxyribose. Amino sugar. This is pretty much like any sugar molecule except that it has an amino group, NH2 group. And particularly this one is called beta D glucosamine. This is beta because this is carbon 1, OH is on the left. That's why this is beta. Now cell surface carbohydrates called glycoprotein. Now glycoside links to OH groups in proteins are seen in this kind of compounds. Like blood types, we know about blood types AB, AB, O. And we would try to give you a background of these blood types and which bloods are compatible. Now, during transfusion, scientists will have to be, or doctors will have to be careful about it. Now, blood type A is compatible with A, AB, but not O. On the other hand, if donor type is B, is compatible with B and AB, but not O. If blood type is AB, is compatible with AB, not O. On the other hand, if donor blood type is O, every blood type is, as an acceptor, would be acceptable. A, B, AB, or O. Now, composition of blood type has a polysaccharide. So it's very important that we understand this sugar chemistry. Now, type AB has both A and B markers. Now, these are something that characterizes a particular blood type. Here we are showing you composition of blood type A, B, and O. In each blood type, you can see that there are some sugar units present. L-fucose has 6-deoxygalactose, so each blood type has that. In addition, you have D-galactose present in every blood type, D-galactose, D-galactose, D-galactose. Blood type A has N-acetyl D-galactosamine. So there's an amine group there. Now, which blood type B or O doesn't have. So that's the difference. Blood type B has 2 galactose units, whereas O has only 1 galactose unit. And keep in mind, these are all bonded to protein. That's how you get different blood types. In last slide, we have shown you that blood type O has 3 sugar units. That's why it's called trisaccharides. On the other hand, A and B, they have 4 sugar units bonded, and that's why it's called tetrasaccharides. Something in common is all these sugars have galactose, and very commonly present. Then deoxygalactose, and also there is an amine group attached to the glucose. So these are the common features of present in all these blood types. Now about sweeteners, if sucrose gets number 1, then it's interesting to see that lactose or milk sugar is only about 0.16. Glucose is close to sucrose in sweetness, about 0.75. Fructose is about 2 times sweeter than table sugar. Fructose is nothing else but called fruit sugar. On the other hand, artificial sugar, aspartame, is 180 times sweeter than sucrose. Saccharin, which in this country, is not being used anymore, which is about 350 times sweeter than sucrose.